Hi, I'm Brian Pruitt, tutoring high school physics. Today's topic, mirrors. There are three major kinds of mirrors you'll encounter in physics: plane mirrors, concave mirrors, and convex mirrors. So let's look at plane mirrors first. These are simple. They're just a straight line that's going to reflect light. So you have light coming in, and it has an incident angle. It'll come out at the exact same angle. You can extend the reflected rays back through the mirror to form our image over here. It's going to be the exact same height as our original object. Note also that the distance between the object and the mirror is the same as the distance between the image and the mirror. On to the curved mirrors. First up, concave. If you want to remember what a concave mirror looks like, note that it looks kind of like the opening of a cave. So let's take this apart. We have a focal point and a center point. What does center point mean? Well, if you extend the ends of a concave mirror, it'll form a circle, and this C is going to be the center point of that circle. So essentially, the distance between here and the center point is the radius of that circle. Half of that distance is the focal length. Focal length is extremely important for mirrors. Often in physics, you'll be asked to find an image based on an object, such as this one. So there's three rules that you're going to need to find out where an image is. First up, you only need two rays to find out where the image is. Second, a ray that is parallel to the axis is going to reflect through the focal point. Third, a ray that reflects through the focal point is going to reflect parallel to the axis. So let me show you what I mean. We have our object. First off, our parallel ray is going to reflect through the focal point. Next up, our ray through the focal point is going to reflect parallel. It may help to do this with a ruler. And so where these 2 points intersect is where our image is going to be formed. Notice I've extended the rays from the head of our object, so this is going to be the head of our image. And we have it there. Alright, next up, convex mirrors. So these are curved just like concave mirrors, but in the opposite direction. And so if we extend this in a circle, we get our center point over here on the right side of the mirror instead of the left. So our focal point is going to be located here. Exact same rules. Parallel goes through focal point, and focal point goes through parallel. So first we have our parallel ray. It's going to reflect through the focal point, but our ray cannot actually go through the mirror. So what we do is we draw a line, a dotted line through the focal point to represent a ray of light that we perceive, but isn't actually there. And the actual ray of light will reflect in the exact same line. And then we draw one that goes to the focal point, so you might want to use a ruler to figure out approximately how that works. And this one's going to reflect parallel. Draw the parallel line, extend that through the mirror, and then where these two intersect is going to be our image. So there's a difference between the images formed here and here. One is real and one is virtual. This one is real because it's formed by light rays that are actually reflected and actually intersect here. This one is formed by apparent light rays, so it's going to be virtual. The light rays aren't actually extending through the mirror, but we perceive them as it, so this is going to be a virtual image. Okay, so let's get into the number of things. First off, everything to the left of the mirror is going to be considered positive. Everything to the right of the mirror is going to be considered negative. True for both concave and convex mirrors. So, neat little cheat you can use. If you have an image distance that is positive, you have a real image. If you have an image distance that is negative, it's going to be a virtual image. So now let's actually take a look at some equations. 1 over the object distance plus 1 over the image distance is going to equal 1 over the focal length. So focal length is the distance, again, between the mirror and the focal point. Let's find out where our image is if we have a focal length of 5 meters and an object distance of 10 meters. So 1 over our object distance of 10 meters plus 1 over our image distance is equivalent to 1 over our focal length. Subtract 1/10 from both sides, you get 1 over our image distance is equivalent to 1 over 10 meters, so then our image distance is just going to be 10 meters. And notice that it's positive, that means it's going to be on the left side of the mirror. Next up, convex mirrors. So you have a focal length of negative 12 meters because the focal point is on the right side of the mirror, so it's going to be negative. Our object distance is positive 6 meters, so you can never have a negative object distance. And we need to find the image distance. Well, 1 over our object distance of 6 meters plus 1 over our unknown image distance is equivalent to 1 over negative 12 meters. So subtract 1 over 6 on both sides, you get 1 over our image distance is equivalent to negative 1/4. We invert both sides and we get our image distance is equivalent to negative 4 meters. So that means it's going to be on the right side of the mirror, and it's going to be 4 meters from the actual mirror. Okay, so one last equation. Magnification is equivalent to negative image distance over object distance. So let's find the magnification of this mirror over here, our concave mirror. M is equivalent to negative image distance of 10 meters over here, divided by object distance of 10 meters. And so our magnification is negative 1. That means our image is negative 1 times as big as our object. So it's the exact same size, but the negative means that it's going to be inverted. So upside down image. What about magnification for a convex mirror? Well, over here we have an image distance of negative 4 meters and an object distance of 6 meters. So we run through the division and we get the two negatives canceling out. We get a magnification of 2/3. That means our image is going to be 2/3 as large as our object. But it's positive, so it's going to be all upright. Alright, to recap, there are three main kinds of mirrors in physics that you're going to encounter: plane mirrors, concave mirrors, and convex. Plane mirrors are just a straight line. They're going to reflect light at the same angle at which it comes in. If you extend the parallel rays back through the mirror, the ones that are going to reflect, then you're going to be able to form your object. The distance between the object and the mirror is the same as the distance between the image and the mirror. Concave mirrors look kind of like a cave. If you extend the ends out and form a circle, you can find a center point. Half of the center point is the focal length. You'll often be asked to find out where the image is going to be given an object. In this case, you're going to draw rays. You only need two. Draw a parallel ray, and that's going to reflect through the focal length. Draw a ray through the focal length, and that's going to reflect parallel to the axis. Where these two intersect is where an image is going to be formed. Exact same rule for convex mirrors. Note, however, the focal length is on the right side of the mirror, and that you're going to extend rays through the focal length through the mirror, but these are not going to be actual light rays, they're going to be apparent. Real images are formed by actual light rays reflecting. Virtual images are formed by apparent light rays intersecting. To quickly figure this out using numbers, if your image distance is positive, then you have a real image. If it's negative, then you have a virtual image. Okay, everything on the left side of the mirror is going to be positive, everything on the right side of the mirror is going to be negative. And now, 1 over the object distance plus 1 over the image distance is equivalent to 1 over the focal point. And finally, to find the magnification of something is equivalent to negative image distance over object distance, where negative magnification refers to an upside down object. Alright, that's all for now. Again, I'm Brad Prier. See you next time.